Thank you for presentation and thanks for organizing this great event in these difficult times. This is a theoretical work. It's devoted to new mechanism of magnetic interaction in the superconducting system. And therefore I begin from the brief review of known mechanism of magnetic interaction mediated by the superconductors. Proposed law equation, if we take spin wave with two magnets and superconductor, the antiferromagnet configuration is more favorable because destructive effect of each magnet in the superconductor partially compensate each other, and therefore for sufficiently thin superconductor this configuration more favorable. This effect is due to the proximity effect, and therefore it works only for thin layer of superconductor, not larger than the coherence length. For the nodal superconductor, this distance can be greatly enhanced. Probably Angelo Di Bernardo talked about this today. Other mechanism is due to the electromagnetic proximity effect. In this mechanism, if we talk without details, all due to the magnetic field in the superconductor, and therefore characteristic scale of interaction is the magnetic penetration depth. This mechanism usually also prefer antiferromagnetic orientations of the to these magnets in the spin wave. All this mechanism restricted in scale by the coherence length or magnetic penetration depth, that is, they sufficiently short-ranged from our point of view. Also, a lot of literature about the interaction between magnetic impurities in the superconductor, but it's slightly different physics, and I will not discuss it. And once more, from our point of view, this sufficiently short-range interaction, and we, in our work, predict a new mechanism which much more with the scale of interaction much larger. It's practically macroscopical. The system which we consider is simple. It's two coupled Josephson junction. Each of them is a junction with anomalous phase shift and magnetic interlayer. This system is controllable by the external Josephson phase chi, and key ingredient of this system is the anomalous phase shift in each of the Josephson junction. That is, the current phase relation for each of them is the next, where chi naught is the anomalous phase shift. It's proportional to the magnetization of corresponding magnet in y direction, and R is a coefficient which is proportional to, not proportional, which is due to spin-orbit coupling. In different models it will be different, but for us it's not important. We simply take it as a parameter. And as I already say, the main ingredient is the anomalous phase shift in the Josephson junction. And now about experimental observation of such Josephson junctions. To obtain anomalous phase shift, we need simultaneous breaking of invertial symmetry and time reversal symmetry. Breaking of the invertial symmetry corresponds to this vector n, which corresponds to structural asymmetry that is Rashba spin orbit in our system. Js is the direction of the supercurrent in Josephson junction, and breaking of time reversal symmetry is due to the Zeeman field. Therefore, in such a system we can have non-zero Lifshitz invariant, and anomalous phase shift chi0 is proportional such combination. That's why, as a previous slide, chi0 is proportional y component of the Zeeman field. There are several experimental results. The reference for this works where Josephson junction with anomalous phase shift was observed. In all of them used as interlayer some material with strong spin-orbit coupling, the surface states of topological insulator, quantum dots, nanowires, and so on. But in all of them, Zeeman field was obtained with the using of external magnetic field, and it's not sufficient for us to manipulate and control magnetization by superconducting phase, and to our effect, the next step from the experimental site is required. We need in Josephson current with the anomalous phase shift, where the Zeeman field is due to the proximity with the magnet. The possible candidates for this is heterostructures with the ferromagnet and topological insulator, nanowires proximized by magnets, magnets with intrinsic spin orbit. So it's possible, but not realized yet. Now, if we have one Josephson junction with anomalous phase shift, how it can be used to control magnetization? Here the usual standard current phase and energy phase relation for usual Josephson junction. If we have anomalous phase shift, it changes such a way. Here green and red curves correspond to different orientation of the magnet. And if we consider only slow process, when the magnetization in the Josephson junction can adjust itself to minimize the energy, therefore we can obtain the next sufficiently strange pictures for current and energy of the system. This is also current phase relation and energy phase relation. Upper one is for the case when the magnetization can be only along or opposite y direction, and bottom is for the case when the magnetization is free and can be in any direction. Nevertheless, in both cases we can see that we easily can choose magnetization by choosing superconducting phase or by choosing supercurrent. If we take this phase, we obtain up magnetization. Is this, we obtain down. That is, in one Josephson junction with anomalous phase shift, we can easily manipulate by magnetization of this junction. But we want not manipulate by interact of two magnetization. Therefore, We in our system take two Josephson junction with magnets as interlayer. M1 and M2 is a unit vector in the direction of magnetization. Both these Josephson junction with anomalous phase shift. We suppose that the middle superconductor is sufficiently long, so we take into account the gradient phase in it. It's proportional to the supercurrent. And then all this system is controlled by the superconducting phase between the end of the system. Okay. In such system, the energy is simply the sum of the Josephson energies and the magnetic energy. Here is we take magnetic of with easy axis anisotropy. It's in the y direction because it's most simple and simultaneously most interesting case for us. Then, using current conservation, we can exclude the phase of the middle superconductor and obtain the energy of the system, the final expression for the energy. And in this expression, we can see that energy is a function at fixed superconductor phase. Energy is a function of two parameters, M1 and M2, that is y component of magnetization of both magnets. Here simply a graphical representation, that is pictures of the energy as a function of this magnetization for several regimes. There are three several regimes. First of them, when the magnetic anisotropy energy is sufficiently large, this one. In this situation, only magnetic configuration with magnetization parallel or anti-parallel to y direction is possible, these red points. But when we change the phase, all these pictures slightly differ, but always this configuration separated by high potential barrier, and therefore it's not convenient to manipulate them. If we reduce the magnetic energy, that is takes smaller this term, we obtain the next situation when some of these corner states are stable, other unstable, and this picture change when we change the superconducting phase. There are also other possible situations with more complicated situation with non-aligned solution, but we in this short talk not discuss it. Then we work only in this situation. It's most interesting for us. Now I show this energy of these corner states for different superconducting phase difference. Different colors correspond to different magnetic configurations. Red and green is parallel configurations, and blue is anti-parallel as a function of the phase on the system. You can see that by choosing superconducting phase, we can easily choose any magnetic configuration. And the ground state of the system is up, down, down here, antiferromagnetic here, and up here. In the vicinity of the ground states, the current is small, and we can expand expression for energy by this value, and if we do it up to second order and then express all in the terms of magnetization, we can obtain this approximate expression for energy, and it's very convenient to analyze. At first, this term is simply individual interaction of magnetization with the phase. It's very similar to situation in the single Josephson junction with anomalous phase shift. These terms dominates at the large phase difference and results in the fact that at large phase difference only parallel configuration exists.
Alexander, sorry to interrupt, about 5 minutes, yeah?
This term is simply correction to the magnetic anisotropy energy, and this term is most interesting for us. This is a direct interaction of magnets with each other. Sign of this term positive, it's prefer antiferromagnetic configuration, and it dominates at the small phase difference. So at small phase difference, magnetic main configuration is antiparallel. Now about dependence of this effective coupling constant on the distance between the magnets. Distance dependence is a constant kappa, which correspond to this gradient term. And this value is proportional to the distance between the magnets, and from this we can see that at large distances interaction proportional to inverse square of the distances, and characteristic distance is of order 1 millimeter, that is macroscopic value. At distance less than this millimeter, practically no distance dependence. If we take into account inductance, then this law change to inverse in the L on -1. Some comment: parallel or anti-parallel configuration is not in real space, but with respect to superconducting line. Here, anti-parallel configuration in the real space can be seen such way. Also, we calculate dynamic of the system, as I have not sufficiently time. I will skip this and only show this slide. If we start from the equilibrium situation, which prefer antiferromagnetic configuration, and by hand switch one of them, the system restores the antiferromagnetic configuration and switch other magnet. That is direct confirmation of the interaction between the magnets. And with this I conclude. We predict mechanism of long-range antiferromagnetic interaction via the superconducting phase. The mechanism is based on the magnetoelectric coupling between the superconducting phase and the magnetization. The interaction strength is not restricted by the macroscopic size, it can be on the macroscopic distances, and the total magnetic configuration of the system can be controlled and manipulated via the superconducting phase. All this in this paper, and thank you for your attention.
Thank you.
Thanks. A very short question. What is the typical time scale of
Time
switching?
scale.
Yes, I mean, because you show some numbers, but these are just simulations.
Excuse me, I don't.
The typical time scale, in case you have to implement this, what would be the milliseconds, microseconds? Yeah, here, for example. Yes. Yeah, exactly.
Сейчас in Landau-Lipschitz-Gilbert, we take Landau-Lipschitz-Gilbert equations. This one, from it obtains the characteristic time, and in these units of order 2 order larger than this time. Okay? On the graphics, here the characteristic time of switching in these units. T0 is time of rotating in the anisotropy field.